Hi everyone, in this talk, I will present the paper Rethinking Domain Generalization for FAS Anti-Spoofing, Separability and Alignment. Nowadays, FAS authentication systems demand a high level of security. For example, hackers can use your photo to unlock your personal mobile phone. FAS anti-spoofing has then become an important topic. However, FAS is a challenging problem in the wild. Because FAS images come from complex scenes and different devices, where it is hard for our model to learn all the domain variations. Most prior works regard the domain-specific signals as a negative impact and remove it, which may lead to the inconsistent live-to-spoof transition across domains. In this work, we keep the domain information while aligning the live-to-spoof transition to be the same for all domains. Our algorithm consists of two parts. Subcon is used to separate the feature and IRM helps align the live-to-spoof direction. We include both quantitative and qualitative results to verify the superiority of our framework. Now let's start with the problem setup. Our learner has access to a set of training data from multiple domains. Each image corresponds to a binary label, either live or spoof. In the test time, the model is asked to predict the live or spoof of the input from a new domain. One can view the cross-domain FAS as a special binary classification problem to distinguish live and spoof faces from an unseen domain. Prior solutions like SSDG or SSAN consider domain-specific signals as a confounding factor for model generalization and hence aim to remove domain discrepancy from the feature representation. However, feature space becomes ambiguous when domains are mixed together. If features from different domains are collapsed together, the live versus spoof classifier will undesirably leverage spurious correlations to make the live or spoof predictions. Such a classifier will unlikely generalize to a test domain when the correlation does not exist. In this work, we rethink feature learning for cross-domain FAS. Instead of constructing a domain-invariant feature space, we aim to find a generalized classifier while explicitly maintaining domain-specific signals and aligning the live-to-spoof transition to be the same for all domains. Achieving the ideal feature space requires overcoming two key challenges. The first challenge is separability. We need to encourage features from different domains and live-spoof classes to be separated, which facilitates maintaining the domain signal. The second challenge is to align the live-to-spoof transition to be the same for all domains. We proceed by showing the details of our method. We first introduce the model architecture, which consists of two components, deep neural network encoder phi and a classifier beta with a weight vector that maps the embedding to a scalar value, or a binary cross-entropy loss can be applied. The challenge 1 considers the separability in the feature space that encode the input space by neural network phi. We characterize the domain separability as supervised contrastive learning or subcon. Subcon aims to learn a representation space Z that gathers samples in the positive set Px while repelling samples in the negative set Nx. It naturally suits the need for the cross-domain FAS setting, since we treat samples with the same domain and with the same live-spoof label as the positive set and they will form a cluster. We exemplified the idea by comparing the feature visualization with real examples. In the figure, different colors represent different domains. Different shapes represent live-spoof labels. We see that feature gets more separable by applying the subcon loss. Now we move on to discuss the second challenge, how to align the live-to-spoof transition across domains. We propose to formulate the alignment problem as invariant risk minimization or IRM, which aims to jointly optimize the feature space phi and the hyperplane beta as shown in the objective below. Now we introduce in detail why the IRM objective can align the live-to-spoof hyperplanes. If we ignore the constraint, the objective is equivalent to the original empirical risk minimization or ERM, which is a common strategy that merges data from all training domains and learns a predictor. And what if we just apply the ERM loss and ignore the constraint? It turns out that the feature in different domains can be arbitrarily shuffled, as we showed in the toy example. In those cases, the live and spoof samples are perfectly separated. However, the live-to-spoof transition is inconsistent among all domains, which may hurt the generalization ability to an unseen domain. When the IRM constraint is satisfied, it requires consistency between the globally optimal hyperplane, beta star, and the domain-wise optimal hyperplanes. In this case, the live-to-spoof transition is aligned. Then the question left is how to optimize the IRM objective and obtain the ideal feature space. We propose a new algorithm using the projected gradient descent. Due to the time constraint, we do not expand the discussion here and include more details in the paper. Now we present our experimental results. We use the ResNet 18 as backbone and evaluate on 4 widely used datasets: ULU, Garcia, Replay, and MSU. Following prior works, we treat each dataset as one domain and apply the leave one out test protocol to evaluate their cross-domain generalization. We compare the most recent baseline methods in the chart. Our method SA-FAS outperforms the rivals by a significant margin on cross-domain FAS benchmarks. Note that the numbers in the chart follow the convention in prior works, which are reported on the training snapshot with the best performance. However, it may fluctuate on the test set, and hard to truly reflect the generalization performance. To provide a fairer setting, we propose to report the average performance from the last 10 epochs upon convergence. SA-FAS still largely outperforms its rivals, which further validates the superiority of our method. In the paper, we also provide UMAP visualization of SA-FAS feature space from the penultimate layer. We see that the hyperplane between live samples and spoof samples is consistent across different training domains and also transferable to unseen test domains. In summary, we first offer a new perspective for cross-domain FAS by designing the feature space based on separability and alignment. Secondly, we also exploit the domain-variant representation learning by combining contrastive learning and optimizing invariant risk minimization or IRM through the projected gradient algorithm for cross-domain FAS. Thank you for listening. Our code link is available if you are interested.